Alright, so we're going to look at Griffiths quantum mechanics, problem 2.46. This is the case of a bead with mass m that is allowed to freely travel around this frictionless circular hoop of wire or whatever, or it could just be constrained to move in a circular path some other way. Alright, let's see. So he tells us that it's basically just like a free particle, except for a periodic boundary condition, just meaning the wave function and its derivative have to match up with itself when you go all the way around the circle. So just a couple of notes about this before we get into it. The way Griffiths has this set up is he gives it to us in terms of L, so big L, which is the circumference of this loop of wire or constraint, whatever. All right, so you can imagine if we were to stretch this out, we would have a length of big L. So one note about this is, and we'll see this in the solution, is this is basically like an infinite square well, except it doesn't have to go to 0 at the ends. It just has to match up with itself at the ends. So just as an example, for the infinite square well, you can have if we put this end at the origin of our position, for the infinite square well we just get sines. So all the cosine terms go to 0, right? Because cosine doesn't equal 0 at the origin. But in this case, the cosine term can still exist. So just as an example, looking at so for the infinite square well, we can get a sine wave like this. Suppose our infinite walls would be at this point. But in this case, let's see if I can draw this. We can get this, but we could also get something like this, so a cosine. Right? So it still matches up with itself just fine. So anyway, so that's one piece of this. So we're going to be solving this in terms of this big L coordinate that, which is again just the circumference around the hoop. So we're going to be treating this as our coordinate will be x, from 0 out to L. But we could also do this with a coordinate of angle, so theta. All right, so just in your Hamiltonian, use angular momentum about the axis coming out of the page, right? So instead of the position x, right? So our momentum, our angular momentum, this would go into the operator minus I h bar d by d theta. All right. So we could do this either way. We'll stick with the way Griffiths does it, but essentially the forms of the equations are the same. It's just there's an x instead of theta. All right. So let's get into this. So he gives us kind of a place to start. He says this is just like a free particle, except for the periodic boundary condition. So I'll skip the Schrodinger equation and everything. Let's just write out the equation for a free particle. So we just have e to the I kx and some other constant multiplied by b to the minus I kx. All right, and k is the 2me over h bar, and the top is under square root. All right. There's no v in here because the potential is 0. So here we go. Now we just have to meet a couple of boundary conditions. Okay, so we have 2 boundary conditions that we have to meet. We know that the wave function must be continuous at the boundary, and also its derivative. So the wave function, and also its derivative. Like so. Let's go ahead and write these out. So I have a e to the I k x plus b e to the minus I k x equals a e to the I k x plus L, b e to the minus I k quantity x plus L. All right. Let's go ahead and write the second one here real quick. So we're just going to take the derivative of this. So we have an I k a e to the I k x plus negative I k b e to the minus I k x equals an I k a e to the I k x plus L minus I k b e to the minus I k x plus L. All right, so let's just go through real quick. So one thing we can do here, we can just pick a location for x. So we're basically just picking our reference point at which point, so here, you know, if we're using this x coordinate, not the theta, we pick this point on the circle to be our x equals 0. And then x is going off in this direction. So let's go ahead and set a 0 point. All right, so I'm just going to set it just set x equal to 0, okay? All right, so this one will come down here. All right, so setting x equal to 0, these ones, the exponentials will go to 1, so we get a plus b, all right, equals, and then we don't, splitting this into 2 exponentials, it's going to go to 1 again, this other term. So we just get a e to the I k L plus b e to the minus I k L. All right, and now looking at our second boundary condition. So one thing we can do right away is divide by I k, right? And then we're also going to set x equal to 0. Pick our origin. So that looks just like this, except there's a minus sign. So a minus b equals a e I k L, okay, minus b e to the minus I k L. All right. Here we go. All right, so let's just go and to eliminate, to rearrange these equations, let's add them together and also subtract them. So adding them together, we get we get a 2a equals, okay, these parts will go away. We get a 2a e to the I k L. All right, and then subtracting this equation from the other one. Now the a's will go away, and we get a 2b equals 2b e to the minus I k l. All right. So when Griffiths talks about these two independent solutions for each energy corresponding to clockwise and counterclockwise, these are sort of what he's talking about. So supposing, I mean, A or B, could go to 0, but supposing that they don't, in order for these equations to still be true, we have to have these exponentials go to 1. All right. So what this means is that, so this puts restrictions on k, right? So let's just look at the first one real quick. So e to the I k l equals 1 when k l is equal to a 2n pi, where n is an integer. So whether that's 0 on up. All right. And so for this other case, we would get basically we get a minus sign in here, so we can have negative integers as well. So now we're not just talking about positive integers, we're talking about any integers. So k, which once you multiply by h bar, gives you the momentum of the particle, right? That can be positive or negative. So here's where we get our clockwise or counterclockwise solutions. All right, so in general, the solution is going to be a superposition of these other two solutions. But we do have to talk about normalization. So one thing we know is that if we have a solution which is equal to a sum of some coefficients and some wave functions, we're assuming that our coefficients, right, once you take the absolute value squared of them and sum them up, assuming your coefficients are normalized and your wave functions are normalized, so that each of these wave functions, when you take the absolute value squared, each of these is also normalized, then our final answer will be normalized. So here we have these two, if I can put my hand here and look at these right here. These are like our two wave functions. So what we want to do is normalize these individually, so that way we can meet this criterion, all right? And then when we mix them together in different, as long as the way we're mixing them, our coefficients add up to 1, or the squares of them, which, right, they do when it's always like 1 over square root of 2 and 1 over square root of 2, things like that. As long as then our coefficients behave, we get those all add up to 1. Basically all the probabilities add up to 1, right? Then our final, most general wave function will also be normalized. All right, so basically what we're doing is we're just looking at this, we're looking at meeting this criterion. So, so that's why we're going to take these individually and normalize them. So I'm just going to keep using the A and B in this case, just to do this. So, so we'll get E. All right, so we're integrating all the way around the circle one time, 0 to L. All right, and we get so we get an e to the I k L, and then multiplied by the complex conjugate e to the minus I k L. All right, those just cancel out and go to 1. All right, and we're integrating with respect to x. All right, and we are forcing this to be equal to 1 for our normalization, and then we'll find out what A is. All right, well, like I said, this part just gives a 1. They divide out. So what we end up with is an A mod squared, and so that's a constant, comes out of the integration. When we integrate with respect to x, that's the only thing there. We just get x evaluated at L and 0. We just get L equals 1. So this tells us that A is equal to 1 over L under a square root like this. Okay, so our most general solution to this problem is going to be, well, let's write out the pieces first. So he says we should call them a plus and a minus. Okay. All right, so put our 1 over L square root out front, and then e to the I k L. All right, and k, we solved for that, right? 1 over L, let's write this out again, e to the I. Okay, and then, so k is equal to 2n pi divided by L. So this L is going to divide out 2n pi. Okay, so here we go. And then, and it can be any integer, I guess positive integer if we want this to keep going the same direction. All right, and I think we have enough space to go ahead and write out the other one here too. Like this. All right, so let's see, let's look at the energy real quick. Right, so we found the stationary states right here. What are their energies? E sub n is just going to be b squared over 2m, which is equal to h bar k squared over 2m, which is equal to, so we have an h bar squared, we have a 2m, and then we just have to square k, which we, again, was 2 pi n over L. 2 n pi over L, this is squared. All right, so this is equal to, we will have a 2 on the top, and n squared pi squared, h bar squared, squared, h bar squared, okay, and then we have an m on the bottom, and an L squared. All right, so here's our energy. All right, so why is this case different from, let me just read you, he says, how do you account for this degeneracy in view of the theorem in problem 2.45? And why does the theorem fail? Okay, so the theorem, he says, in one dimension there are no degenerate bound states. That's the theorem. So ways to look at that. So normally in one dimension, to normalize something, it has to go out to 0, out at infinity. Here, though, we only have a finite range for this. I guess you could also look at this and just say, yeah, it's one-dimensional in the sense that that we're only dealing with one coordinate x, right? But it's a little weird in the sense that this would have to be two-dimensional if we're just talking about from a physical standpoint. It's kind of, so mathematically it may be sort of one-dimensional. Mathematicians may disagree with me, but in order to get a boundary condition like this, you have to have two dimensions, right? So you can wrap around and meet back up with yourself. So it's not, I'm probably on thin ice here, but in my mind it's not really just simply a one-dimensional problem, because with the toroidal boundary condition that we have, in order to wrap around and meet back up with yourself, in my mind, you can't really just do that with just one dimension.